All right, today is a whole lot of review of trigonometry, things that we should have learned in geometry last year. So the first one is the Pythagorean Theorem. Next, we'll learn about the two special right triangles, the 45-45-90 and the 30-60-90, and their properties again. And then we'll talk about right triangle trig, which you might remember as Sohcahtoa. Okay, so all of that is in today's lesson. It's all review, so it is going to be a little bit fast and a lot of information. So if you do have access to a printer, printing out the sheet will save you a little bit of writing for sure. All right, so reviewing Pythagorean Theorem. Pythagorean Theorem says if I have a right triangle, meaning we have a 190-degree angle, that the two sides next to my right angle are called our legs. Okay, and the Pythagorean theorem, these are not necessarily equal, sorry, I was just marking them. But it says that the sum of the squares of the two legs equals the square of the hypotenuse, which is always the longest side in a right triangle. Okay, so the hypotenuse is always kind of opposite our 90-degree angle. And we know, of course, a squared plus b squared equals c squared, where a and b are interchangeable, but the hypotenuse has to be c. Okay, so if we use that on our two special right triangles here. So our first one, our 45-45-90, we have two equal sides. The legs here are equal. Okay, so knowing that, if I call one of them x, we can call the other length x because they're the same. And if we use Pythagorean theorem, a squared plus b squared equals c squared, we can find a property that will always be true for the hypotenuse. So let's check that out. X squared plus x squared, this is our a squared plus b squared, equals our unknown length here, c squared. So let's say we're going to try to solve for c to find what this length would equal. So 1x squared plus another x squared makes 2x squareds. Next, I would need to square root both sides. And normally, of course, we would put plus or minus here for an even-numbered root. But because c is a length, and lengths can never be negative, we're only going to use the positive case. Okay, so those cancel out. And we get c equals the square root of 2 times the square root of x squared. Or the square root of 2x squared, of course, but you can separate them as individual radicals. That's one of our properties of radicals. They separate over multiplication and division. Anyway, so whether you separate them or not, when we simplify this, we have a pair of x's, which means we get to take an x out of our radical. So you can either think of the square root and square here cancel, or that we can take an x out of our radical. Either way, we end up with x times the square root of 2 is the length of c, the hypotenuse. So if this side length is x and this side length is x, the hypotenuse will always be x times the square root of 2. So for instance, if I said this is 5 and this is 5, this would be 5 times the square root of 2, right? Some nice, easy ratios to follow. Okay, our next one is called the 30-60-90 right, special right triangle. And this one actually starts from, if we started with a model for it, if you start with an equiangular and equilateral triangle where all the sides are the same and all the angles are 60 degrees, 60, 60, and the top is 60 as well. And you draw in an altitude, which makes a right angle from one of the vertices with the opposite side. Well, that ends up bisecting the angle up here, cutting it into half, and this becomes a 30-degree angle. Not only does it bisect that angle, it actually bisects this side. So in fact, this side length ends up being half of this length, but remember, all three sides were initially equal. So what that means is this length is kind of half of this side length. If we're just looking at this right triangle in here, this 30, 60, 90, and that's where this comes from. It's actually half of this equilateral triangle. So we get this ratio that this shorter side, because again, this kind of comes from this equilateral triangle where this length, and this length were equal, but this side got cut in half. Okay, so anyway, so if we call this length x, the hypotenuse will be twice x. That is something that's always true for this triangle. Now again, because we know something about two sides, relating them to the same value x, we can find a value that's always true for this other side. Okay, so in this case, this would be my hypotenuse, or c in the Pythagorean theorem. So let's call this a. We're going to say a squared plus x squared equals the hypotenuse 2x squared. Well, 2x times 2x is 4x squared. And if we move this x squared over, well, that's 1 less x squared. So now we have 3x squared. And like we did before, we're going to take the square root. Since a is a length, we only want the positive value here. And just like before, we're going to be able to take an x out of our radical because it's x squared. So this simplifies as x times the square root of 3. So this missing length up here can be filled in as x times the square root of 3. So if this length is 4, okay, the smaller length, we call this the shorter leg, because in this triangle the legs are different lengths. We call this the short leg. This is referred to as the longer leg, and this is the hypotenuse. So the shorter leg is 4. The hypotenuse will be twice as big, 2 times 4, or 8. And the longer leg would be 8 times the square root of 3. So it's just x, the shorter leg, times the square root of 3. And so this kind of shortcut is a very fast way to find some missing lengths in special right triangles. If you have a 45, 45, 90 or 30, 60, 90, you don't necessarily have to do the full Pythagorean theorem. In fact, if you only know one length in these two triangles, you can find the other two using these properties. All right, well, let's do some examples. Find some missing sides and some missing, using our special properties. So here we have a 45, 45, 90. And again, if you remember, the two legs in the 45, 45, 90 are equal. So if that one's 5, the other is 5. And to get to our hypotenuse, it's just 5 times the square root of 2. In fact, the exact example I used earlier. Now what about if I need to go backwards, right? Think about here, we kind of needed to multiply one of these lengths by the square root of 2, right, to get to our missing length. Well, what if I need to go backwards? What if I know the hypotenuse? I could divide by the square root of 2. In fact, you can even think of this 11 root 2 divided by root 2. Those cancel and we get 11. Or you can just use pattern recognition, right? This happened to have the root 2 with it, so that number in front of root 2 is x, or our length of our legs. So once again, of course, another 45, 45, 90. If we divide by root 2, we can find the length of a leg, and our other leg will be equal. Okay, well, we can use this idea to go from a hypotenuse that doesn't have the root 2 with it and still find these missing legs. So again, following our pattern, we know to get to the hypotenuse, we'd multiply by root 2. So to go backwards, let's divide. So if I do 10 divided by root 2, now you might remember we're not supposed to leave radicals in the denominator. And the way we do get rid of that is we multiply top and bottom by root 2. So we get 10 root 2 over 2, which actually simplifies to 5 root 2. The 10 and 2 outside the radical can be reduced. So in fact, this ends up being 5 times the square root of 2, and this leg ends up being exactly the same. Okay, try this out for, say, D. See if you can figure out the length of our other two missing legs here, and unpause the video. Okay, so this one, the fraction can't be reduced, right? 7 halves. But same idea, we divide by root 2, so we put 7 over root 2, and then we rationalize the denominator. We multiply top and bottom by square root of 2, so we get 7 root 2 over 2, and this time the 7 halves does not reduce. So it's just 7 root 2 over 2 for both legs. Okay, let's move on to our 30, 60, 90 properties. So kind of the key here is the shorter leg. So again, this is called the short leg. This is our longer leg. And then we have the hypotenuse, right? So if you know the short leg, it's really fast to get to the other two. Double it to get the hypotenuse, multiply it by root 3 to get the longer leg. So my goal is always to get back to the short leg if that's not what I started with. So for example, E, they did start us with the shortest side, so it should be easy to find the hypotenuse. We double it to find the hypotenuse and multiply it by square root of 3 to find the longer leg. So we're just following those two patterns there. Okay, well, what if this time they started me with the hypotenuse? Well, remember, the relationship between the hypotenuse and shortest leg is that the hypotenuse is twice as big. Again, instead of multiplying by 2 to go this way, we can think of it as dividing by 2 to go the other way. So the shortest leg is 6. We now have the short leg, which is the key. So to find the longer leg, it's the short one, 6, times the square root of 3. Okay, G, you might do sight recognition and recognize that this is a number times the square root of 3, which follows kind of our long leg pattern. And that's fine. Or think of, again, if I knew the short leg, to get to the longer one, we multiply by square root of 3. So if we need to go backwards, we would divide by square root of 3. So 5 root 3 divided by root 3, the root 3's cancel, and we get 5 as our shorter leg. Double it to get the hypotenuse, and our other length is 10. Okay, here's one. It's kind of similar to how we did C and D, but following our pattern for the 30, 60, 90. See if you can figure out H, and then unpause the video. Okay, so for H, if you divide by root 3 and rationalize, multiply top and bottom by root 3, you get 7 root 3 over 3, and that 7/3 does not reduce. To find the hypotenuse, we need to double the shorter leg here. So multiply it by 2, or 2 over 1, and only the 7 on the outside will be the only number that doubles. So we get 14 root 3s over 3. Okay, next up, let's review some right triangle trigonometry, Sohcahtoa. And what this is supposed to help us memorize is the 3 right triangle trig ratios. So is sine of our angle equals the opposite over the hypotenuse, O over H, opposite over hypotenuse. Cosine of our angle equals the adjacent, so that's the A, over the hypotenuse, which is the H. So there's our cosine of our angle is the adjacent side over the hypotenuse. And tangent, our third trig ratio, is equal to the opposite over the adjacent. Tangent of our angle is the opposite side over the adjacent side. Okay, so the first thing you want to do when you're solving one of these is pick one of your 2 acute angles, so not the right angle, but one of the other 2, and we would label this as our angle of reference, called the reference angle. Okay, and we use that to label the 3 sides as the opposite, adjacent, and hypotenuse. So the side opposite is either across from our angle, or it's the only side that angle does not touch. The hypotenuse is always opposite the right angle, and it's always the biggest length in our right triangle. And adjacent just means next to. So in other words, this is the side that's next to our angle, but not the hypotenuse. Okay, so let's use that to set up the first one for A. Find our missing length, x. So note that we have a right triangle. So first thing I'm thinking is maybe Pythagorean Theorem. However, I don't know 2 out of the 3 sides. I don't have enough information for Pythagorean Theorem. So next I would think maybe I can use my special right triangles. But with a 47-degree angle, it's not a special right triangle. And so here is where I would know, okay, now I need to use Sohcahtoa, or right triangle trig. So they've given me one of the 2 smaller angles, and even though you could solve for the missing one, remember these 3 add up to 180, you don't need to. Let's just use the angle they've given us. So that's my reference angle, and we need to label our 3 sides. So for me, I like to label the opposite first. So opposite my angle would be x. Oops, so this is the opposite side. 12 is the hypotenuse, right? It's across from my right angle. hypotenuse is over there. And then this side is the adjacent. Okay, now if you have like all of these pieces of information or more than just these two, you can kind of pick your own. But here, we're going to go ahead and say which one is not very helpful for us in this problem, or not important. Well, we know the hypotenuse. That gives me a number. That sounds important. And we're solving for the opposite, right, which is x. So these are the two that are important to us for this problem, the opposite and hypotenuse. So now I think Sohcahtoa. Which one involves the opposite and hypotenuse? So, ka, or toa. In this case, that's so. And what that means is that sine is the trig function we want to use this time to solve for our angle. And as we set this up, we say sine of the angle theta equals, of our angle equals the opposite over the hypotenuse. Okay, so here we're going to go ahead and fill in our angle. Our angle is 47 degrees. Equals the opposite side, which is x, over the hypotenuse, which is 12. And I always suggest this, that to make your life easier when it's not as simple as this particular one, if you set this up at being over 1 and cross multiply, so kind of treat it like a proportion problem, x times 1 is x equals 12 times the sine of 47 degrees. Okay, now the sine of 47 degrees is a decimal value that we can get from our calculator. We'll learn later on where that comes from, but for now, we just need to use a calculator. So here's where we bring in, say, Desmos. Okay, so important, first, there's a little switch here. Make sure that you're in degrees, so you can see DEG. Otherwise, you're in a angle measuring unit, radians, which we'll talk about again. So degrees, and I want to do 12 times, and you'll actually see sine, cosine, and tangent right here, which is great, sine of 47. And as long as this is in degree mode, it knows that means degrees. And this is the length of my missing side, 8.776, etc. So it says round to the nearest hundredth. So that's 2 decimals, but remember we'll need to look at 1 and more to figure out how to round. So here we need to round up. 8.78. 8.78 is our approximate missing length. And that seems reasonable based on my figure, right? We already know the hypotenuse, so it should be slightly smaller, and it seems pretty reasonable. Okay, if you get an answer like 112 in this figure, I'd hope you'd go, that doesn't sound reasonable. Okay, B though. Let's try another one. So here, again, they've given me one of my two angles. Or I guess if I went through my checklist, I can't use Pythagorean Theorem because I don't know 2 out of the 3 sides. It's not a special right triangle, so now I'm thinking right triangle trig, Sohcahtoa. So here's my angle of reference. Let's label our sides. This side is the side opposite, so that would be our 5. The blank one over here is the hypotenuse because that's opposite my right angle. And down here would be the adjacent side, where x is. So this time, the one that doesn't really help us very much is the hypotenuse. So I'm thinking the 2 I'm interested in are the opposite, which I know, and the adjacent, which I'm solving for. So A and O, or O and A. So I'm thinking Sohcahtoa. Which one uses A and O, or O and A? Toa, which means tangent. So this time, tangent's the trig function that will help me figure this out. So, oops, I wrote the sign. So tangent of our angle, theta, equals the opposite over the adjacent. So filling that in, we can say the tangent of 20 degrees, that's our angle, equals the opposite side, which is 5, over the adjacent side, which is x. And here's where some students run into problems, and this is where I say, if you cross multiply, make this a fraction, and cross multiply, we're going to end up with x times the tangent of 20 equals 1 times 5, or 5. And to get x by itself, well, tangent of 20 is held with multiplication. We just divide both sides by tangent of 20 degrees. So in fact, to get my answer, I need to do 5 divided by the tangent of 20 degrees. And I need to do that in my calculator, or Desmos. Okay, so we'll bring that back in. Here's our calculator. So I'm going to delete that 5 divided by, and again, it's always good to make sure it's in degrees, since we're using degree. Now you can actually type in tangent, I think. I'm just going to go ahead and click this anyway. And we'll type in 20 and 5 divided by the tangent of 20. Again, we're going to go to 2 decimal places, so we'll need to round up once again. 13.74. X is about 13.74 units of length. Okay, so this is how we can use Sohcahtoa to help us find missing side lengths if we can't use Pythagorean theorem and can't use special right triangles, and it's a right triangle. Sohcahtoa, or right triangle trig, will help. Now we can also use this to find missing angles. Now note here, I do know 2 sides, so if we really wanted to, we could find the third side with Pythagorean theorem, but we're not asked to find a missing side, we're asked to find the missing angle. And so here's where these trig ratios will help us again, but we're also going to need to use what's called the inverse sine, or inverse cosine, or inverse tangent. And we saw this inverse notation, right? Like f inverse of x, right? Meaning inverse, that -1. So that is inverse notation. Now these are also sometimes called the arc sine, arc cosine, and arc tangent. They mean exactly the same thing as inverse. So anyway, just so you're exposed to those a little bit. But let's use this to find my angle. We've been given an angle. Let's mark that as our angle of reference and label our sides. This is the opposite side. 24 would be the hypotenuse. And the blank over here is the adjacent side. Because it's blank, I'm figuring that's not really going to be very helpful. We can just get rid of that one. So I'm thinking the 2 most helpful we know are the hypotenuse and opposite. Now, by the way, if you did know all 3 sides, that's okay. Just pick 2. Pick your favorite 2, and that will tell you which trig to use. Just pick one. Anyway, here, O and H goes along with sine. We need to use sine again. Sorry, cosine. So here we're using so or sine. So the sine of our missing angle, theta, equals the opposite, which is 9, over the hypotenuse, which is 24. So this is from our so, right? Sine is the opposite, sine equals the opposite over hypotenuse. Okay, now note that our angle is locked inside this sine function. Well, how do we get to cancel out sine? We need an inverse sine. And so guess what we're going to do to both sides of the equation? We're going to take the inverse sine of both sides. So that would look like this. We take the inverse sine of theta and the inverse sine of 9/24. So here, the inverse sine and sine cancel each other out. And we're just left with theta degrees is equal to the inverse sine of the fraction 9/24. So the inverse, when we're using inverse sine in the calculator, we're telling it, we're giving you a ratio and we want the angle. So again, we'll go to, say, Desmos. Now to get to the inverse ones, they're not on the main page. You need to go to functions. Go to functions, and then you'll see inverse sine, cosine, and tangent, or arc sine, arc cosine, arc tangent. So here we're going to do the inverse sine of 9 divided by 24. And this ratio, by the way, sine can never be bigger than 1. So you probably saw it said undefined until I wrote 24. So this value always has to be less than 1 for sine, or equal to 1. So 9/24 gives me an angle, and we're going to round to the nearest tenth. And in this case, that means I will not need to round up. We're going to write 22.0 degrees. About 22.0 degrees. Now the reason we're leaving that extra 0 there is to let anyone know that we did go to the accuracy of the tenths place, but that we didn't need to round that to a different digit than 0. Okay, and by the way, now that I know one of these, I could find the other by subtracting from 90, right? If that's about 22 degrees, this would be, what's 78, right? 78 degrees. Subtracting from 90. Anyway, because these three should add up to 180. All right, let's move on to the next one. Our last one here, we've got a reference angle. We're labeling our sides. We got the opposite, we got the adjacent, and we got this hypotenuse, which does not seem very helpful. So see you later, hypotenuse. Opposite and adjacent means tangent again. Man, sorry, cosine. All right, so TOA, the tangent of our angle in degrees equals the opposite over the adjacent, 12 over 5. Just like before, we would do the inverse tangent of both sides. Okay, so we get theta is equal to the inverse tangent of 12/5. So once again, we go to Desmos, we type this in, inverse tangent of 12 divided by 5, and we get that our missing angle, going to the nearest tenth or 1 decimal for angles, is 67.4 degrees, about 67.4 degrees. Okay, so obviously we'll go over more questions about this in class, or go over more examples in class. But important things. These are all things that you should have learned. I know that last year was a little bit weird, but these are all things you should have learned in geometry last year before you left. So they are a little bit of a review. Thank you guys. We'll do some in class. See you next time.